Hello, this is the luckiest maths teacher in the world. Thank you so much for tuning into this video on experimental probability. So last time we looked at theoretical probability, which is the fraction or proportion of times something should happen. And today we're going to look at experimental probability, which is the fraction of times something actually happens. And this is very useful because sometimes it's really hard to calculate the theoretical probability. So let's use the example of the Brisbane Broncos. What's the probability they'll win a given game? Well, that's a really hard one to judge. You might say, okay, there's a 1/3 probability they'll win, 1/3 probability lose, and 1/3 probability of a draw. But you could then say, well, hang on a minute, in rugby league, if it's a draw, it goes to extra time, so there's probably a greater chance that they'll win or lose than they'll draw. There are so many other factors, though. You know, the Broncos, they always seem to lose when they play the Storm, but they always seem to win when they play the Sharks, so it depends on who they're playing. It probably depends on whether they have their best team there or players are injured. We can't really give a number to the theoretical probability that they win. But in 2019, they won 11 out of 24 matches. So that gives us some indication of the probability they might win their next game at the start of the 2020 season. We might say it's 11 out of 24. Now that won't be a perfect guess, but it just gives us some idea. So now we're going to look at an example where we're definitively calculating the experimental probability of something. I rolled a die 10 times and I've listed the results. And what we're going to do is calculate the theoretical probability, which is TP, and the experimental probability of a variety of events. So let's start with the event that I got a 1. The theoretical probability is 1/6, because there's 1 on the die, 6 in total. And that's the same for 2, 3, 4, 5, and 6. So that's what should happen. I expect I'll get 1, 1/6 of the time, 2, 1/6 of the time, and so on. But of course, that's not what actually happened when I rolled the die 10 times. So you can say I got 1 3 times. So the experimental probability, it happened 3 times over 10 times in total. And that's just common sense. So to calculate the experimental probability like I did just there, it's the number of times it occurred over the total number of trials. So there were 10 trials here, 10 times I rolled the die, and a 1 occurred 3 times. You can see that 2 occurred once, so its experimental probability is 1/10. Same for 3, it occurred once, so 1/10. 4 occurred once, so it's 1/10. 5 occurred once, so it's 1/10. And then 6 occurred 3 times as well. So its experimental probability is 3/10. So note that the experimental probability was different than the theoretical probability for all of these outcomes. And that's okay. The experimental probability won't always equal the theoretical probability. Now, all of these should add to 1 because they are all the possible events. Probabilities add to 1, just like percentages add to 100%. And if you added up all those numbers, you would get 1. What we're saying essentially is I got 1 30% of the time, I got 6 30% of the time, I got 2 10% of the time, and so on. They need to add up to 100%, and 100% is equal to 1. So now we're going to look at some other events. So what's the probability that I would roll an even number? The theoretical probability is a half, or 3/6, because you have half a chance, 50-50 chance of getting an even number as you do an odd number. So the theoretical probability of an odd number is also a half. Now, in our experiment, we actually did get the experimental probability to equal the theoretical probability. Because in my rolling the die 10 times, I got an even number 5 times. I got 6, 6, 2, 6, that's 4. And then I got a 4, which is the 5th time. So there were 5 times that I rolled an even number out of 10. And of course, that is equal to a half. Okay, and similarly, for an odd number, it was 5 out of 10 or a half. So once again, these two probabilities should add to 1 because they're the only possibilities in the sample space. I either get an even number or an odd number. I can't get anything else. And once again, they do add to 1. So this time, the theoretical probability did equal the experimental probability. So what is the probability of getting a number greater than 4? Well, normally I'd expect that to happen 2 out of 6 times because there are 2 ways it can occur. I can get a 5 or a 6 out of 6 in total. Note 4 is not greater than 4. So the probability, theoretical probability of getting a number greater than 4 is 2 out of 6 or 1/3. So in my rolling the die 10 times, I got a number greater than 4 on 4 occasions. 1, 2, 3, 4. I don't include 4 because it's not greater than 4. So 4 out of 10, which is equal to 2 over 5. So in this case, the experimental probability didn't equal the theoretical probability. Sometimes they're equal, sometimes they're not. So now we're going to do another question that's a bit more reasoning type. Please pause and copy this down if you need. So I perform this experiment, which I have a bag of marbles. I take one randomly without looking, put it back. I actually did this 100 times, and these are the results. I picked out a red one 25 times, a yellow 47 times, a green 18 times, and a blue 10 times. So I'm going to estimate the theoretical probability of each. So this is where experimental probability can be useful. When we don't know or can't calculate the theoretical probabilities, we can rely on the experimental probabilities. So the experimental probability of picking a red was 25 out of 100. So I can guess that the theoretical probability will be close to 25 over 100, which is a quarter. So similarly for yellow, I can guess that the theoretical probability will be similar to 47 out of 100 or 0.47. It might even be a half. This is just an estimate of the theoretical probability. So similarly for green and blue, I'll estimate their theoretical probabilities as 9 over 50 and 1 over 10 respectively. So that's how we can use experimental probabilities to just give us a guess as to what the theoretical probability might be. So now we're going to do a different question. Please pause and copy down the bottom if you need it. So now I'm saying that the bag actually contained 20 marbles, and I'm going to estimate how many were red, yellow, green, and blue. So remember, that's okay because I put the marble back each time, so I could still perform the experiment 100 times. So let's look at red. So I got red 25 out of 100 or 1/4 of the time. That was its experimental probability. So I'm going to guess that a quarter of the marbles were red. A quarter of 20 means a quarter times 20, which is 5. So I'm going to guess there were 5 red. Now, I could do the same for yellow, but the thing is, if I do 47 over 100 times 20, I actually get the number 9.4. So there can't have been 9.4 yellow marbles. So I've got to guess a number close to that. So there's probably either 9 or 10 marbles. So I might say 47 out of 100 is close to a half. So I'm going to guess that there were half the marbles were yellow, so that there were 10 yellow marbles. Okay, so for green, something similar, 18 over 100 times 20. Again, it won't give me a whole number, 3.6. So I'd guess there were 3 or 4 green marbles. So I might guess that there were 3 green marbles. And then for blue, I got 10 over 100. 10 out of 100 times I got blue. So 10 hundredths of 20 is equal to 2. So I'm going to guess that there were 2 blue. So, of course, 10 plus 5 plus 3 plus 2, all of these numbers here should add to 20, and they do. So that's a reasonable guess. I can't say for sure how many of each there were. There could have been, 15 red, 3 yellow, 1 green, and 1 blue. There could have been that. I just don't know. So now we're going to look at the link between the experimental probabilities and possible values for the theoretical probability. Again, please pause and copy down the bottom if you need. So we have 5 statements here, and we're going to go through each one and determine whether it's possible or impossible. So firstly, it says, is it possible that the theoretical probability of red is actually 1? So let's think about what that means. If the theoretical probability of an event is 1, that means it is certain to happen. That means every time we picked a marble, we should have got red. We didn't. We actually got yellow, green, or blue. So it is not certain when we pick a marble that we would get red. So what that means is that this is impossible. We can't have that red was certain because we didn't get red all the time. So second, the theoretical probability of red is 0.9. So that's just saying that it is much more likely you get red than any of the other colors, that we're really likely to get red. Now that's possible. It's not likely, but it is possible that 90% of the marbles in the bag were red, even though we only got red a quarter of the time. Like I said, possible but not likely. So 3, the theoretical probability of red is 0. This would mean it was impossible to get red. Given that we actually did get some red marbles, it can't be impossible. So this cannot happen. We can't have had the theoretical probability of red is 0. So note, if we're talking about the theoretical probability of red, all we can say is that it definitely wasn't 1, it definitely wasn't 0, it is possible that it could be any number between, but not including 0 and 1. So fourth, the theoretical probability of purple is 0.2. Well, I didn't actually pick any purples, but that doesn't mean necessarily that it was impossible. I didn't look at the back, so I don't know whether there were any purple or not. So it is possible that 0.2, which is 20% of the marbles, were purple. Just because I didn't pick any purple marbles, it doesn't mean that it was impossible. So for 5, this is probably the easiest of them. The theoretical probability of blue is greater than that of yellow. So I got substantially more yellows than blues, but that doesn't necessarily mean that there were more yellows in the bag than blues. Sure, it's unlikely that there were more blues than yellows, but it is not impossible that there were more blues than yellows. So this one is absolutely possible. Again, all we know about the probabilities of blue and yellow, they can't have had a theoretical probability of 0, they can't have had a theoretical probability of 1. Other than that, we can't say anything about them. We don't know which actually was more likely to be picked, we just know which was picked more often. Alright, I know that this reasoning stuff can get a little tricky, so please let me know if you have any questions. First 5 people from my class to say lollipop and reference this video, you will get one. Thank you so much for watching. This has been the luckiest maths teacher in the world. Have a great day.